Hello, everyone. This class, we're going to continue with our learning on the computational methods in engineering. Specifically, we're going to talk about linear algebra and introduce the different data types in MATLAB. So this is sort of a mixture of two chapters. So if we do a quick recap of our last class we talked about inputs and outputs of the user-defined functions. So it's basically overall, it's everything about user-defined functions. We talk about the different kinds of inputs or outputs. It can be numeric, it can be strings, it can be multiple inputs, multiple outputs, or no inputs or outputs. Then we introduced different handles, which is the at sign. And then we talked about how to use F0 and Fsolve to find the roots of the function. And we said that Fsolve is actually can be used to solve different sets, a whole sets of different types of linear or nonlinear equations. And of course, Fsolve will take a little bit longer time. And there are functions to find minimum and maximum of the functions. And we can also find the points that represents the minimum and maximum. And we also did some different methods for calling the functions. And the most the fastest way is actually to define the function in advance and use the function handle. And we introduced different additional functions like the anonymous function, which are not saved as the M file, and then also the subfunctions, which are saved in the primary function, just following the primary function in the M file. So these are the different aspects of the user-defined functions. So in this class, we're going to talk about the linear algebra. So specifically regarding how to solve sets of linear equations. So remember last class when we were saying that we could use F0, right? F0, but it's limited by the fact that it can only solve the equation that has one variable. And we can also we can also use Fsolve to solve sets of like a set of different equations, nonlinear or linear, but normally it takes longer time. So if you use the tick-tock function and then try to find that actually Fsolve is I would say it involves more heavier computation, right? So then in this class, we're going to introduce how MATLAB uses these linear algebraic methods to solve sets of linear equations. Okay, so you may wonder, why do we need to solve these sets of linear equations? And actually, if you have went through the class of, my previous classes about environmental engineering, so on the chemistry aspect, actually, we said that in the beginning, we need to understand this stoichiometry, right? So when we talk about stoichiometry, it's going to be about the balancing of equation. So this is the example that we used at that time, right? So this is the reaction of nitrogen dioxide with water, forming nitric acid and nitrogen monoxide. And if you directly look at these terms, right? So there's no obvious solution because oxygen is everywhere, nitrogen, right, appearing multiple times, 3 times, and then hydrogen, right? So then we said that at that time, to balance these type of equation, we have to find the unique element, right? The unique element is actually water. So we can assume that here the stoichiometric number in front of water is 1, and that's why you have a 2 in front of the nitric acid. And then we try to build up an equation, right? So we assume that there is X number of nitrogen dioxide and Y number of nitrogen monoxide, and we can start to build the equation for nitrogen, right? X of nitrogen equals 2 plus Y, and 2X, this is for oxygen, 2X plus 1 equals 6 plus Y, right? So you end up having a set of linear equations. This could be a simple example, but once we involve more sophisticated, let's say the organic reactions where it involve carbon, hydrogen, oxygen, right? These elements are so basic that they can appear everywhere on the left-hand side and right-hand side of this chemical reaction. So then you may end up having a whole set of linear equations. So here in this class, or the beginning part of this class, we're going to talk about how we can use these built-in, let's say, MATLAB function to solve these sets of linear equations. Okay, so basically here you can see that we have x minus y equal 2 and 2x minus y equal 5. So if you try to simplify this into a sort of the form in a matrix calculation, then you can basically simplify it as, let's say, 1, or let me just write out the matrix here. You can define a matrix of 1, minus 1, and then 2, and minus 1. So this is our matrix, right? So you sort of have this relationship of A multiplied by X and Y listed as the, let's say on the right-hand side, equals 2 and 5, right? Because if you have X and Y here, when you do the matrix calculation, it's going to be 1 multiplied by X minus 1 multiplied by Y, which is 1 minus Y, right? That equals 2. And then 2x, 2 multiplied by X minus 1 multiplied by Y equals 5, okay? So basically, you are trying to solve the equation of A multiplied by, let's say, X, Y equals 2, 5, right? So then you could, so the overall goal is, let's say, to find out the solution that basically satisfies A multiplied by this solution, multiplied by these variables equals 2 and 5, right? So then basically here, I'm going to introduce you different ways to do such a calculation. So let's use this example. This is a more sophisticated example, right? So you have 3 unknowns, 3 equations. Okay, so then it involves X, Y, and Z. And if you do the similar conversion of this mathematical equation, then you have, you can define an A matrix being 3, 2, minus 1. Right? There's a typo here, 3, 2, minus 1, and then minus 1, 3, 2, and then 1, minus 1, minus 1. And then X having X, Y, and Z. And B is 10, 5, and 1, minus 1. Right. So then you can use the calculation. Basically, the most obvious or most direct way to do the calculation is you can minus the inverse of A, right? So if you do the inverse of A, then you have inverse of A multiplied by A equals just 1. And then, so you have X equals inverse of A multiplied by B, right? So if we do the definition here, let's say we inverse this matrix 3, 2, minus 1, as we said, minus 1, 3, 2, and then 1, minus 1, minus 1. Okay, so then to do the calculation, basically X is just inverse of A multiplied by B. This is mainly because if you multiply an inverse of A, right, A to the power of minus 1, which is inverse of A, then you end up having 1 here, right? So that's directly you have X on the left-hand side being inverse of A multiplied by B, right? So we also have to define B. B is 10, 5, minus 1. Okay, so then if we do the calculation, this is our answer. X, or the X, Y, and Z equals minus 1, 5, and minus 6 respectively, right? So then I would say that this problem here, this is basically giving you a finite answer, right? Give you a correct answer. But there could be scenario, let's say that the equations are just repeating itself. For example, this can be 2 equations, right? 2 linear equations. But the second equation is nothing but the multiply of the first equation. You just multiply 2 on both the left-hand side and right-hand side, you end up having the same equation, right? So under this situation, you actually call this call this set of problem as a singular problem. Basically, there is no unique solution, right? So you can have any combination of X or Y, right? So if you plot this equation in a mathematically in the plots, right? So if you have 2 lines that can cross each other, then it means that it's non-singular. It has a finite solution. But then if you have the scenario where, let's say, basically this problem, this is not a singular problem, right? This is not just simply multiplying 2 to the solution, right? But then on the other hand, let's say if you have this equation, right? If you have this set of equation, you have 2 times of the left-hand side equals a different value, right? If you have a different value, then it's singular and doesn't have any solution, Okay, so basically on the left-hand side, these two terms are the same, but it doesn't make sense that on the right-hand side, these two terms do not follow this two times of the relationship, right? So because of that, this set of solution doesn't have solution. This set of equations doesn't have solution. So we call this problem as the singular problem, right? So there could be singular problem that has having no unique solution. There could also be singular problem that has no solution, right? So this is no unique solution because you can have any combination of x and y, okay, as long as they follow this relationship, because this equation just the double of this equation. And then for this problem, right, we also call it singular, but it doesn't have a solution because the conditions contradict each other, right? So you said this term equals 5, then the double of this term should equal 10, but it's actually 3, which means that it has no solution. Okay, so this is the singular problem or non-singular problem. And in MATLAB, basically it can only solve the non-singular problem. If you have a singular problem, then it's going to report an error. Okay, so then we could actually generalize the singular or non-singularity of the equations. So for example, if you have this set of equation, right, 6x plus ay equals 0, 2x plus 4y equals 0, and then when you take the difference between these two equations, right, so then you have basically multiply 3, right? You multiply 3 to the second equation, take the difference, and then the solution is y equals 0 only if a is not 12, right? If a equals 12, then there is infinite number of solution for x and y. Okay, so this is sort of a generalized form to tell whether the equation is singular or not singular. Okay, so then basically, as we said earlier, right, so we could use this inversion method. So this is another example, right? You could have 2x1 plus 9x2 equal 5, 3x1 minus 4x2 equals 7. So you can generalize this equation into matrix calculation that you have 2, 9, and 3 minus 4, and xy on the second term, right? You can name this term as the x, which includes x and x1 and x2, and that equals 5 and 7, right? So then you can simplify this calculation into ax multiplied by b. Note here that a is a matrix, b is a vector, and x is a vector, and b is also a vector. So you have this sort of expression. So how do we solve for x, right? You just multiply by the inverse of a on the left-hand side. And we should pay attention that you don't multiply the inverse anywhere, right? It cannot be inverse of a to be here and inverse of a to be on the right-hand side, because we know that a multiplied by b, if it's matrix calculation, a multiplied by b is not equal to b multiplied by a, right? You don't have this um, independence of the product or the multiplication calculation. Okay, so the minus of a has to be always on the left-hand side. So if it's on the left-hand side, you know the inverse of a multiplied by a is 1, right? And then you just have x, right? So instead of saying 1, it's actually a matrix that only have ones on the diagonal location. So if that's the case, then basically you're just going to get x1, x2, x3, x4, right? You're going to get this matrix that this array that you want. And that's going to be equal to the inverse of a multiplied by b. Okay, so then you can just calculate the inverse of a multiplied by b. For this case, again, you can define a, or it can be any factor, right? You can define that as a lowercase a, 2, 9, then 3 minus 4, and then b as 5, 7. So then the x is just inverse of a multiplied by b. Or let's use the uppercase. Okay, so this is the solution. So x1 equals 2.37, x2 equals 0.0286. Okay, so you can use the command inverse a to compute the inverse of the matrix of A. This is a solution. But if you try to solve a singular problem using the inverse of A, then you will end up having an error. So for example, let's define A being 2 4, and then 4, 8. Okay, so this is, if you see for this matrix, the basically means that the second equation is just the double of the first equation, right? And now if you try to solve this equation, it's going to say that matrix is singular to working precision. So you're going to get an error, okay? So basically in MATLAB, there are other ways to solve the set of linear equations as well. So this is called the left division method. Okay, so this is also called the Gaussian method. So left division method, to do that calculation, you just need to, instead of writing the inverse of A multiplied by B, you can just write A and then a backslash of B. Okay, so let's say we're still using the same example, but use the right sort of matrix, right? So we still have this method, this problem, and then if you do x equals inverse of A multiplied by B, you can have this solution here, right? So you can also use, as I mentioned, A backslash B. This is called left division method. Okay, so you're going to get the same result. Okay, so overall, the left division method is faster compared to the inverse method, because inverse you have to involve how calculating the inverse of a matrix. Okay, so basically this method also works in some cases where the number of unknowns does not equal the number of the equations. So basically you have what people call the underdefined or overdefined equations. Okay, so you can also try this case. For example, A and B are defined as the matrix and array here. Then you can calculate X, right? 7 and 4. So remember the type of the I would say the code or the script you use to calculate the solution here is different, because here is inverse, right? You can understand inverse and multiply by the array, but here you just directly type in the matrix itself and then a backslash of B. Okay, so this is a difference. So then we can talk about this underdefined or overdefined equations. So this equation is actually a properly defined equation. So you can see that they actually don't form these singular problems, because on the left-hand side, none of these terms are just double or triple of one of the equation. Okay, so if you want to do the calculation, you could have, let's say, 3, 2, 5 in the first row, 4, 5, minus 2, second row, 1, 1, 1. Okay, and B being 22, 8, 6. And then you could have the solution being inverse of A multiplied by B, right? Or X being A backslash B, left division, right? So this is the solution you get. So what do we mean by an overdefined equation, right? So basically now we know that there are 3 unknowns, 3 equations, so there is a finite solution. But what if we add one more, right? We add one more equation into this system. And actually right now, this one more equation does not conflict with these 3 here. Basically, this is sort of an additional condition, but the same x, y, and z is still going to make this equation work. So for example, if you have x, y, z being 1, 2, 3, if you plug it in, so you're going to have a 2 here, 2 minus 8 minus 21, right? So minus 8 minus 21 adding up together is 29, minus 29. So minus 21, 9 plus 2, that's minus 27. So basically this fourth equation still can use the same solution. So now if you define the A being 2 minus 4 minus 7. So now since A matrix is 4 by 3 now, so I don't think you can calculate the inversion anymore, because the inversion calculation has to be a square matrix, right? So under this situation, we should use the left division method. Okay, so yeah, we need to include the B, right? So B is 22, 8, 6 minus 27. Okay, so you see that we can't use the inversion method. So then we have to use left division method. let me see. So B, we have to use it, um, define it as a column, right? So you can see that X is still 1, 2, 3. So basically, this additional equation doesn't affect what we are going to get, right? So then what if we make this fourth equation does not agree with, let's say, the original condition, right? So what if we change this value to minus 28? So basically, you may say that why this could be the case, but actually in engineering, there can be many scenarios like this. So, for example, if we're trying to observe an object from, let's say, using different observe the dimension of certain object. Let's say let's say a bridge, right, or distance between two mountains that we're trying to build a bridge. Then one method is to use the satellite imaging, right, to find out the tip of the mountain. And the other method could be use the telescope and then mark on the left-hand side, mark on the right-hand side. And the other method could be you're using laser, right, use the time method, right? So how much time it takes for the light to travel back. And you could use like 10 different types of method, right? But the distance between these two building points is fixed. It's one solution, right? There's only one solution, but you could end up using different methods that just trying to characterize that one single or defined solution, one set of solution. So you will end up having more equations than the unknowns you want to solve. And then the thing is that for each of the method is not free of uncertainty, right? So any method could have an uncertainty, right? So basically what is telling us is that this value could not be 22, maybe 22.1, or this value could be 8.2, right? This value 5.9, right? This value being, let's say, minus 28, right? So there are uncertainties regarding our observations. So that's why it's actually always good to have more equations than the number of unknowns. Always nice to have more number of equations than the number of unknowns so that we can get a better estimate of the final solution. Okay, so then you may say, well, how do we make sure that the final solution is not, well, is as close as the accurate solution as possible? And actually, in MATLAB, for this left division method is actually going to use the least squares approach. So basically, it's going to estimate how far your solution is from the original, let's say, the definition. Okay. So for example, now we're changing this final solution here. Instead of minus 27, let's change it to minus 28. So we just changed this value by 1 here. Okay. And then you can use the same um, let's say, left division method, and this is what you get. Okay, so 0.86, 2.1, right, 3.30. Then you can see that now it's deviated from 1, 2, and 3, right? So then you can plug it in. So you can do A multiplied by X and see what we get on the right-hand side, right? And if you see the right-hand side, basically, it's actually very close to what we have over here. It's not going to be exactly the same value, mainly because there are only 3 unknowns, right? But there are 4 equations. So you see that it cannot satisfy all of the conditions. It cannot satisfy all of the equations, right? Because you sort of over-defined all of these parameters, and you cannot force all of these parameters to, let's say, if you still use 1, 2, and 3, the final solution will not be minus 28, right? Still be minus 27, as I showed over here. So then MATLAB actually used this least squares approach that is going to try different combinations of x, y, and z so that the deviation from these preset equation results or the function results are minimized, right? So that's why it's called least squared approach. So you can see that if you use the new x multiplied by new a multiplied by no as the x multiplied by the new y, and this is what we get, right? 21.99, 7.99, 6.01 minus 27.99, right? So it is very close to this solution or this result, but it's not going to be exact. right? Because there's no way we can fix X, Y, and Z or force X, Y, and Z to satisfy this requirement, right? Which is good because in this way, we actually get more accurate X, Y, and Z from our different methods of observation, right? So we talked about we could use different observation methods to quantify X, Y, and Z, right? So basically, this is the observation results. We can have, let's say, hundreds of observation methods just to characterize what's the distance. Let's say what should be the length, what should be the width, what should be the height of the bridge. And then by having this over-defined set of equations, you can get more accurate results regarding the dimension of the bridge. Okay, so this is an over-defined equation. What if we remove one of the equation, right? So what if we remove the third equation? So now you see that we only have two equations, but three unknowns. So under this situation, if you still use the left division method, right? So let's say we define our A now to be only two rows, right? And then we can have B equals 22 and 8. And then X equals A over B. So we're going to get a solution like this. So note that theoretically, 1, 2, and 3 will still satisfy this equation, right? Because this is no difference from this set of equation. When we showed earlier that this set of equation has a solution of 1, 2, and 3, right? So now, instead of having 1, 2, and 3, it's giving us 0, something, and something. So this is basically the general solution for underdefined equation. So basically, if it's an underdefined equation, MATLAB will always set the first unknown or the first variable to be 0. Okay, so it's not going to set it to be 1. So if it realizes that this set of equations is underdefined, it's always going to set the first variable to be 0. So you can see that if we set this variable to be 0, then you sort of compress or downgrade this equation into a two equations, two unknowns, right? So two equations, two unknown. This is a basically a well-defined equation, right? A well-defined set of equations. So then you could get the exact solution from Y and Z. Okay, so this is about the underdefined and overdefined equations and also how MATLAB solve the problems. So we have introduced this left division method. And actually, there's another way to solve these types of sets of linear equations. So remember, whenever we have these different sets of equations, the first thing or one trick that we will do is actually to reduce the number of variables. Okay, so what I mean is that this is our three equations here. Then what we can do is we can basically use this equation, multiply this equation to make this term to be 0, right? And then eventually we can sort of convert this equation into all ones on the left-hand side. Okay, so this is the what people call the reverse row echelon function, right? Reverse row elimination method. Okay, so you eliminate these terms in the matrix. Okay, so what does it do, right? So you basically we will combine the A term, right, which is the matrix here, and append it by the B term. So you end up having the C equals this term here. And then you will use the rev function, which is reverse row echelon function, right? So eventually you convert this equation into, or you convert this matrix into a matrix that's shown in here, right? Basically by using this addition and then canceling terms, right? So you end up having 1, 1, and 1 in the diagonal locations, right? So then basically it means that the solution is just x equals -2, y equals 5, and z equal -6. Okay, so you could use this function to sort of cancel the factors in your matrix and then eventually get the final solution. So for example, we can still use the same set of definition, right? A equals, right? This is our beginning, right? So, and we also had B equals this thing here. So what the ref function does is It's just going to cancel A and B to the form of you have a diagonal matrix, right? It's a square matrix at the beginning and appended by the canceled sort of the canceled terms on the right-hand side of the equations. So under this situation, the x directly equals 1, y directly equal b, z directly equals 3. Okay, so this is our rev function. So here we can do a quick practice problem. This is about mass balance. Remember, in environmental engineering, we also talked a lot about mass balance. Mass balance involve the balance of the water and also the balance of the material. It could be salt, it could be organics, right? Any type of chemicals. So this is specifically talking about the desalination unit that is trying to purify the water, right? So consider the hypothetical desalination unit shown in this figure, right? The salty water flowing into the unit contains 4 weight percentage salt and 96% water. So inside the unit, the water is separated into 2 streams by a series of reverse osmosis operations. The stream flowing out of the top is almost pure water. The remaining concentrated solution of the salty water is 10% of salt and 90% water, which makes sense, right? So you pull the salt out, and this is more like a concentrated salt stream. So calculate the mass flow rates coming out of the top and bottom of the desalination unit, right? So what is the split of the flow? So this problem requires to perform a material balance, right? So this is the problem where you have basically this amount of the mass of the water going inside the desalination unit, right? So you have the mass fraction of water and the salt, and then on the top stream, you have pure water, 0% of salt. You want to find out what is the flow rate or what is the mass, right? This is talking about the mass, how many pounds are there, and then also the bottom flow, right? So we can build up the mass balance, right? The mass balance is going to be first the water balance, right? So you can calculate the water mass that equals 100% multiplied by x, which is the m tops, we don't know, right? And then plus 90% of the water for the downstream, but the bottom stream. And then you can also build it for the salt, which is 4% of the salt, right? So it's going to be 4 pounds equals here you don't have salt. And then 0.1, which is 10% of the mass for the bottom flow, right? So you simplify this problem into a matrix calculation. So the matrix is going to be, let's say A being 1.9, and then second row being 0 and 0.1. Okay, and your B is 96 and 4. Okay, so then you can just directly solve for what is x, right? So A, you can use the, let's say the left division method, right? We should use the backslash, okay? So 60/40, right? You can also use the our ref method, right? So you just do ref, and then A and B. Okay, so you see x equals 60, y equals 40. Okay? Simple enough, right? So you can use this method to solve sets of linear equations. So note that we cannot solve nonlinear equation here. If it's nonlinear equation, we still need to use the f-solve. But by using this calculation, actually, it's much faster compared to the f-solve because f-solve involves a lot of iteration calculation. Okay, so then in general, the matrix left division is faster and more accurate than the matrix inverse, right? So using both techniques, solve the following equation, system equation, and use the tick-tock functions, right? So what the tick-tock means is that you can start to count the time for calculation, right? So let's say A equals, let's say rand, let's say we're generating 1,000 thousand by thousand random number, and then you type in talk, tick and talk, right? So it takes this long to calculate the, let's say or to create this matrix here, right? So you can do the same thing. Let's first define what is the A here. Well, let's try to type in 3, 4, 2, -1. 1, 7, 1. First row 2 minus 2. Okay, so this is our A matrix, and then we can define our B matrix being 42, 32. Okay, they need to be a be a single column. Okay, always forget about the semicolon here. Okay, so this is our matrix, and this is our sort of the um, the result on the right-hand side, right? So we can do the tick, and then let's say x equals inverse of A multiplied by B, and then okay, so this is the time for the inversion calculation. Let's see, or the left division method. We're going to have A and B. Okay, so it's actually shorter. Okay, so we can also try the cancellation, right? Our ref method. So then you're going to have ref A B. So you can see that our ref, that actually this method is even longer compared to the method, right? So, but overall, all of these times are pretty short because, I mean, nowadays the computation capability is much higher. So a lot of times we may not care too much about the time used here, but still, we should pay attention that the inversion method, right? You have to make sure that your matrix is square. But if you use the left division method, actually the inversion, I mean, the matrix does not have to be a square matrix. Okay. So I think this is about how we can solve the sets of linear equations. And then the next is I would say some operations in terms of the matrix calculation that we can try or we can learn or basically going to be helpful for your homework or for your practice, right, when solving engineering problems. So in MATLAB, remember in the beginning that when we try to do a dot calculation, right? So for example, you define A being 1, 2, right? B being 2, 3, right? If you want to get a element by element multiplication, we said that we can use the dot multiply by y, or dot multiply by b, right? But what if you want to get a summation, right? So not only multiply together, but also sum all of these, right? So one method is that you have the X matrix, you have the B matrix, you can make the B matrix to be a vertical matrix, right, or vertical array, right? So you just multiply together. So what I mean is that you can make B being the transpose of B, then use X multiplied by B, right? So then you get the summation. But actually, if you have two array, let's say you have long arrays, right? And then you want to get the summation of the array after you do the multiplication, you could just use a function called the dot, okay? So what that means is that, let's say you have, um, so basically if you have let's say a matrix of A, right, multiplied by B, and then you want to get the summation of all of these elements, and then you can just use dot A and B. So A here can be actually a matrix, right? So B is can be an array. So what that means is that, let's say we have A being defined as a random number, and then it's a 4 by 4 random number, right? And then B being an array, because random number 4, 1. Okay, so if you want to get the summation, let's say this row multiplied by this column, right? This row, this column, and second row, this column, third row, this column, fourth row, this column, and then get the summation, and you can just do dot A, B. Hmm. Or yeah, let's say when you have the B, you also need to define B as the same dimension. Let's say B being and 4. And then now if you do that, and then you basically get the summation. Okay. So I think by using this example, maybe we can get a clearer understanding, right? So it's often useful to think air is as a single substance with a molecular weight determined by weight average of the molecular weights of the different gas present, right? With little error, we can estimate the molecular weight of air using calculation only including nitrogen, oxygen, and argon, right? You can use the dot product to calculate the molecular weight of the air, right? So theoretically, it's just the fraction multiplied by molecular weight, right? And add them together, right? So then basically you can define A to be 0.78, 0.21, 0.01, and then B being 28, 32, 40, right? So you can directly use a dot, A, B, to get the weighted average. Okay, so I would say most of the time, actually, when you're calculating the weighted average, it's easier to just use a dot A and B, or you could just do sum of A dot multiplied by B, right? So because dot multiply will do the elemental element by element multiplication, and then if you do the sum, then it's also the summation. But the dot multiplication or the dot function is actually more, it's faster, right? It's easier to use. Okay. So I would say that's it for the section related to the linear algebra, right? So we talked about the dot products at the end, and then we talked about solving sets of linear equations, AX equals B. Note here that I should probably use the bold, right? So to indicate that these are matrices and arrays. Okay, so there are different ways to solve the sets of linear equations also, right? You can use the inverse method. You can use the Gaussian elimination, right, which is the left division method. So the left division method, we actually prefer this method, right? So then the reverse row echelon function, right? So this is the way that can cancel all different terms on the left-hand side, right? So you can directly get the answer from the matrix. And then we talked about these over-defined and under-defined equations. And then we sort of introduced why we could have a scenario where we have over-defined equations because there are different observations. So one example that I always show in my aerosol, right, air quality research project, air quality class is that, for example, people are trying to observe the size of a particle, right, and size and concentration of a particle. Then actually people invented these instruments that can conduct measurement at multiple locations using multiple voltages to sort of split this particle of the same size and same concentration, right? So in this way, if you use like different voltages, right? So basically different voltage means different observation methods, right? So then you're targeting at the single size distribution, right? So you could easily end up having multiple, way more equations than what you need in terms of the unknowns. But in this way, you also reduce the uncertainty for each of the observation, right? So you will get actually more accurate results by using these more equations for the observation because each observation comes with uncertainty, right? So you cannot, I mean, it's not recommended to just use one method that inherit its own uncertainty and directly use that as your solution. Okay. So this is it for the uh, linear algebra. And then for the rest of the time, we're going to talk about different types of the data in MATLAB. Okay, so far we have talked about the string, the character, right? Last class we talked about the output, input. There are numeric, there's matrix, there's array. So MATLAB can handle different types of the data types, right? So for example, character, there can be character, just A, B, C, like letters. You can also convert character to strings, right? There's a logical variable when we talked about the different structures of the MATLAB codes, right? Numeric, then there's further integer or floating point. So whenever we use sort of show the integer only, right? So then it's just, it doesn't have any numbers after the decimal point. And then there are also floating point numbers. Remember when we did the when we're talking about the format of the output of numbers, right? So there could be different numbers of digits after the decimal point. You can also specify the precision of the number, right? So double precision, single precision will allocate different bytes or different space for you to store the numbers. And then there's categorical type, the time data type, right? Can be date time, can be duration, and then symbolic. Okay, so this is another table that's showing that in terms of MATLAB array types, if you have an array, what can be the different types of data? It could be categorical, character, logical, numeric, time, symbolic, right? And then in terms of multiple data type, you can also combine different data types into a single variable, right? You can use table, cell arrays, structure arrays, or maps. So in this class, we're going to talk about these common data types and then talking about the advantages or disadvantages that you can use, you can understand. So in the future, you can use the proper data type to store your data. Okay. So first about the numbers, the single or double precision, right? So you probably already know this from your other programming courses. So single or double will determine how much space you assign to this number and also determine what can be the maximum and what can be the minimum of the number that you can use in the calculation. For example, if it has a single precision, then you can do this, use this function, real max, to find out what is the maximum number that's allowed under the single precision, right? You can see it's 3.4 multiplied by 10 to the 38, or real mean, right? 1.1 multiplied by 10 to the minus 38. But if you use double precision, which is the default precision type in MATLAB, then you can go up to e to the, or 10 to the power of 3.308, 308, right? The same thing, the minimum 10 to the power of minus 308, right? So you can see the double precision can cover a much wider range of the number. And this also means that if you have a result that has 10 to the power of 400, right? So A equals this, and then A will just simply be infinity, right? So you can try something like near the edge, right? So 1 multiplied by 10 to the power of 308, you can still define that, right? But if you define that as 1.9, then it's going to multiply by 10 to the, if you define that as 1.9 multiplied by 10 to the 308 power, right, then it's going to become infinity. Okay, so next is the integers, right? So the integers, I have to say that we normally use it, we don't use it for actual calculation. So although sometimes we may end up having an integer in our solution, it's still being shown as the double precision, unless you specify it as the single precision. Okay, so people normally use the integers when they're trying to analyze plots or analyze images. Okay, so you can see that basically if you let's say if you convert the number 10 into an integer, right? So int 8 means the 8-bit signed integer, right? So it only assign 8-bit to store this number here. So if you use, let's say, e equals int 8 of 10, right? So then you see that here, the class, it's int 8, right? So it's still saved as 10, but since you only assign 8-bit to this number, right? So we know that each bit is a binary, it's 0 or 1, right? So it cannot go really large because the maximum will be 2 to the power of 8, right? So which is 64. So that's why if you just directly put 100 there, or let's say we try bigger ones, or 1,000, right? So you can see that the maximum is 127. It cannot go more than 1,000, right? So you may say that, well, if it's only going to 127, why do we still use that, right? So why do we still use this data type? Why can't we just use double precision everywhere, right? It turns out that a lot of times, especially for our screen, right? So when we are trying to show color, we don't need really large numbers to represent the color. Okay, so we use these integer arrays to store image information because we can use that for grayscale or use the integer number to show the RGB, red, green, and blue. So this is an example. So all of the numbers that we see on our screen can be represented by these integers, right? So it's RGB, red, green, and blue, right? So for example, red is shown in here, right? So if you think about it, right? So for each of the color, if all of these color only need these three numbers, that is limited below 256, then we can just show these numbers as what? Int 16, right? You don't need a large space. You don't need a large space to store the color information, right? So in this way, you can actually shrink the data storage we need to show the images, right? So that's why the integer number or the integers are still very important in the programming. Okay, so the next is character and string data. So here, this is just, I mean, at the beginning, you may think that character and string are the same, but actually characters are combinations of single characters, right? Single letters. So the example can be H, let's say H equals holy, right? So you can see this is holy. And then in terms of the size, it's 1 by 5 characters. So actually holy, this although sounds like a string, sounds like a word here, but it's actually an array that has 5 elements in there. So if you do H of element 3, right, you'll see that it's actually L. You can even access what is letter in there. But then actually you can convert this wholly into a string. So let's say K equals string of H. So now K, you can see that now it's in the double quotation sign, right? And then if you check the data type of K, it became 1 by 1. So this is now a single element array, right? That has the class of string. Okay, so basically now you cannot access K of 5 anymore. You can only access K of 1, which is the holy, right? So you see the difference. And then the other thing is that you can actually convert so for all of these um, letters, they're actually saved as numbers because eventually computers are dealing with binary numbers, 0 or 1, right? So basically, you can convert these letters or these characters into numbers. So an example can be, you can convert the character of A. You can see that this is 97, right? This is what people call as the ASK2 type of let's say the conversion of the character into the numbers. This is how computer recognize different letters, right? So eventually it's just numbers and then eventually converted to the binary. So um, basically you can also convert numbers to letters, right? You can just use the character and then convert, let's say 98, because 97 is A, 98 is going to be B, right? Um, so so this is difference, right? So if you type in a word, right? If you use single quotation, then it's a character array, right? So the string saves the entire vector of the character as a single element. Okay. So you can also combine different strings. So for example, if you have two string or two character arrays, let's say we still have the H being holy, and then let's say we have H1 being, let's say, young. Okay, so then let's say that we try to form an array that combines holy and young. It doesn't work because this one has 5 elements and this one has 4 elements, right? So if you want to concatenate it, let's say create a new array of H and H1, right? It's going to say that they're not consistent unless, let's say, we define H1 as young 1. So in this way, they can be combined. So you see that now if we want to combine character arrays, they have to have the same dimension. But for strings, it's not a problem because for strings, each string that we defined earlier is a 1 by 1, right? So it doesn't care how long the string is, right? So in this way, you can easily just use, let's say, string L equals string, and then you can define, say, holy, and yeah. Okay, so you're combining the two strings as, let's say, this string array. And then this is 1 by 2 string array. And you can now access, let's say, L of 2, right, which is young, L of 1. And now you can also see how do we access the certain elements of the string array. We actually use this curly bracket to access certain elements from the string arrays. Okay, so this is basically the example. You can have 5 different names, and then you can try to combine them as a character array, and you're going to get the error that their dimension is not as consistent. So then you could use the method of converting using the character, right, the char here, right, to convert it into a character array. So basically, what the char here does, or the character does here, is that it's going to fill up the extra space as 0 for all of these names or all of these character arrays, right? Another way is to just use a string function. Then the string function does not care, let's say, how long each of the let's say the character array is, right? So you're not going to get any issue with this combination or this concatenation. Okay, so another thing is that if you have this character array and then you're trying to combine with, let's say, the score of each of the student, and then if directly combine the character array with number, actually the combination will turn these numbers into letters. Okay, remember each of the letter here represent a character, right? But if you want to combine them as numbers, then you need to first convert these numbers to strings. Okay, you will use number to string function to convert them into strings, and then you can combine them together. So we can start from just one example. Let's say we can define A. Again, the H is still the holy here, right? So you can try to define, let's say, H together with 100. Okay, so you can see that 100 actually turns the number into D. So what if you want to show 100? Then you are going to use number to string 100. So then it's going to be in this way. So that's what I'm talking about here. So if you directly combine the number with the character array, actually you're going to get the conversion. You're going to convert the numbers into characters. So if you want to combine them as real numbers, then you will need to convert them into strings first and then merge them together. Okay, so the next is a time array. So MATLAB actually has a pretty convenient way to recognize time. Okay, so for example, if you have a string here, let's say 2015 0101. So how does MATLAB recognize this is a time? Right? So if you type in here, actually, this is just numerical, right? So you can add, you can multiply. This is just number. We can convert it into time by just using, let's say, we can convert it into the value of x, and then just use the function of date time. And then you can type in A. This is the sort of the factor or the value that you want to convert into time. And then you will type in convert from. Okay. And then type in the format. YYYY yeah, because it's following the format of year, month, day, right? So now you convert X into the date time. Okay, so it could also be that you're in another country. Let's say, I think in Europe, actually in the US, it's month first, right? So let's say we name another time factor to be B, and then it's January 22nd. Let me see. Yeah, so you see now we also have the issue of 0. We're losing the 0 here. So now let's just sort of name this as November, right? So you still have the same digit. So then how do we do the conversion? We can still do the same, but instead of using year, you can use month, day, year. Okay, so it looks like it doesn't have this type of format. Um, Let me see. Yeah, well, it doesn't have this type of format, right? So let's just practice with this, still the same thing, but then let's do 0, 1, 0, 2. So in that case, you probably need to do some conversion in Excel first, right? In text first, um, or let's say, or you can sort of move these four characters to the let's say to the front or to the back so that we convert that into the YYYY format, right? So you can do that because these are character arrays and you can access these character arrays and move them around. Okay, so now let's say we have B and then we define this Y term to be converting from B to the date time, right? So yeah, we should be using Y, 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 Y. Okay, so this is January. So now let's say we use Y minus X. What are we going to get? So the result is actually a duration. It's in hours, 24 hours, because we know that from January 2nd to January 1st, they're separated by 24 hours. So the data type become a duration. Okay, so basically by using this date time function, in the future, you can convert these time into the actual dates. And then when you're trying to make the plots, you can just do the, let's say, bar or make the plot and use the date as the x-axis, right? And then MATLAB is going to actually show you the actual date for each of the measurement. Okay, so you can see that in the beginning, the date is actually covering each other, and then you can this function, or you can this script to turn the tick x ticks with certain angles, so you can show all of the dates over here. Okay, so basically here I have a hands-on problem. So we can try to plot a list of random numbers, basically generate a random number for each day in January 2025, and then make the plot. So how do we do that? So we first need to define our x-axis, right? So basically the days or the dates, right? So we can just define similar to the values we used here, right? So it's going to be 2025, 01, 01, and they're separated by 1 day, 2025, 01, 31st, right? So this is our x-axis, okay? So then we can do the conversion, right? So date is going to be equal to date time of, how do we define x, and then convert from, and then y, month, date, day. Okay, so this is our x-axis. We said that we're going to make a plot of the date and then a random number for each day, right? So 31, 1, and then in this way. Right, let's connect all of these marks together also. So this is a result, right? This is our random number. It's also showing you the x-axis, right, with the date format. And if you want to rotate this tick marks also, right, you can use the function of the x tick angle 45, which means that you're rotating it by 45 degree. And then this is what you get. Okay, so you can make the plot with the x-axis showing you the date. Okay, so the next is a multi-dimensional array. So basically now, until so far, we only learned about 2D array, right, which is a matrix. But actually, let's say if you have data, time-dependent data, right? So let's say for hour 1, you have this set of measurement, hour 2, hour 3, hour 4. You can create this 3D array or even higher dimension, 4D, 5D, right? So as long as you can imagine it, as long as you can access it, right? So for example, you can create a 3D array, and then you can also create another dimension representing different days, right? Or another dimension representing a different location, right? So there is a higher dimension. Okay, so here, this is an example. If you have a matrix 1, 2, 3, 4, 5, 6, y being 10 times, z being another 10 times, w being another 10 times, and then you can define it. So far, we only use the first two variables. You can create another layer, 1, 2, 3, and 4, right? So now you have 4 layers of data, and each layer shows this matrix, right? So you can use this multi-dimensional arrays or matrices to save time-dependent data sets, for example, videos, or you take many camera images and you can convert them into a multi-dimensional array. Okay, so next is a cell array. So cell array basically can combine different data types, right? So far, when we were talking about combining data sets, they have to be the same type, right? Either the same type of number, right? Where we have matrix, have array of numbers, or array of characters, or array of strings. But can we combine, let's say, numbers and strings into the same array? Right? Actually, that's what the cell can do. So here you have the example of A. Let's say A equals 1 through 3, B equals the string A, B, C, D, E, F, right? C being matrix, right? So 1, 2, 3, 4, 5, 6. So if you directly merge these together, you cannot, right? So for example, if you want to merge B and C together, right, it's going to say that they're not, the dimension is not consistent, right? The type is also not consistent. So then how do we merge these data together? It actually, this could be the case because you could have a data set that has student names and also let's say their score or their calculation results, right? So then you could define a cell. So you can define, let's say, M being your cell, and then use the curly bracket A, B, and C. Okay, so now you have a cell that combines 3 different types of data. All right. So if you want to access the first data, the first element, then this is your array, right? If you want to access the second one, this is your character array. Third one, this is a matrix, right? If you also check the data tab for M, it's a 1 by 3 cell, okay? So then a lot of times, maybe you're confused about what's exactly in the cell. Then you can also do the cell plot of M. Okay, it's actually going to give you this visualization. So the red here represents a number, right? So you have a 1 by 3 numeric array, and then a 1 by 6 character array, and then 2 by 3 matrix, numeric matrix, right? This is a cell array. So for the cell array, the thing is that you can see, let's say here you have these numbers, but you also don't have the annotations for these numbers, right? So of course you can include a string array to sort of note what it means by this array, or another string to note what it means by this matrix. But then are there more efficient ways to sort of combine all of these data together? Okay, so basically to separate each of these data, right? To store them in different variables within a sort of a variable, right? So that is done by the structure array. Okay, so we can still have these ABC here, right? So we know that the A is a matrix, B is our string, C is our A is an array, B is a string, C is the matrix. So we can define a structure by just using, let's say we can define structure. Let's just name it as S, okay? So it can be any variable. So we can do S dot array. Yeah, you can also make it also different names, but now you can sort of give yourself a hint of what is being stored here. Okay, so now the array here, this structure here has this element or this field that has the value of 1, 2, and 3. Okay, so let's say string, being B, and S dot matrix, being C. Okay, so this is our structure now, right? You can see the structure. You can give the field with your own name or your defined name, so you're less confused about what is being stored, right? So actually the structure type of format is quite widely used for storing the data generated from instruments, okay? Because instruments, there are so many types of variables. For example, temperature, flow, right? The pressure, they're recorded as a function of time and also the data that you're trying to collect. Okay, so then it's sort of difficult to save the file as a cell array because if it's a cell array, you don't know what this matrix means because you don't have an annotation, right? But here, actually, you can give it an annotation. You can even name it and include the unit, right? So this is Celsius, right? So you can now you can directly see from the field name what it means, what type of data is included, and also the unit for the type of data, right? So this is the advantage of using the structure. And of course, the structure right now, if you see the S here, right, this is one by one structure. You can also define different layers, different elements of the structure. So let's say we can also define array, young, B, 2, 3, and 4. Okay, so it should be just a normal bracket. Okay, so now you see we have this S here being a 1 by 2 structure, right? So 1 by 2 structure here, and then this is basically the field, different fields, and then the different values. And also you can see that since we predefined the first matrix of S, so it's expecting the same thing. It's expecting the same sort of input from the second element, right? From the second element of the S structure. So that's why it's helpful for, let's say, the instruments to use this type of data because now you can save the data as day 1, day 2, day 3, or different locations. Right, so structures arrays are extremely useful in applications such as data management, since large amount of engineering data are often stored in the database, and structure arrays used for the data analysis, right? Explanatory. So I think the final type is actually the table arrays, right? The table arrays is sort of similar to the structure array because after you convert the table into a variable in your MATLAB database, you can access a table by using the structure format. So for example, if you're trying to, let's say, select what's in the S1, right? So matrix, you can directly use the dot to access it, right? It's going to report you the data. So the same thing for the table. So here we can sort of do an example, show an example here. This is the Denver climate data, right? This is what's shown in this Excel spreadsheet, right? So we can do the similar thing before, like we can import the data, right? This is our data. So remember before when we import the data from the Excel, we were using matrix, right? We were converting everything into numeric matrix. But actually we can directly convert or import them as a table and then import. Okay. So then this is basically the table that we can observe from the Excel spreadsheet. So then how do we access this table? Okay, or access data from this table. So you can directly use Denver. So let's just define this as D. Okay, so this is our D here. You see that D is now a table. So now how do we get the date? So you just directly use D dot and then date, right? So you see that the table array is similar to the structure, right? So you can access the different fields by directly use the dot. So let's say if you're trying to find out the extreme temperature, right? This is the extreme temperature. So now how do we make a plot to convert, let's say to show this temperature, right? Because the temperature each represents a different month. So, and then if we want the x-axis to be showing the date, then you can do plot d dot date, right? Date, and then d dot extreme temperature, right? And the other thing is that here, if you directly make the plot, then the x-axis is numeric, right? So we have to convert it into the date format, which is the date time. And then we're going to use convert from, and then we know it's y, MMDD. Okay, so now you can see that we're showing for different month and then the different temperature, right? So theoretically, you should be using circles because these are real measurements, right? So this is how we can access and demonstrate the table data. So table, I would say, is very similar to the structure, right? So they are self-explanatory, right? It's helpful for us to do the data analysis. Okay, so this is a summary of the MATLAB data types. I think we covered most of them, right? You have the cell array, like character, string, right? Character array, string array, numeric array, symbolic. This one we didn't cover. Logic array, sparse array, we didn't cover. Duration, date, time, category. So I would say symbolic. Um, Actually, we're going to talk about symbolic calculation in our future classes. We're going to talk about symbolic array later. And then it's just the sparse array and then the categorical array that we haven't covered. But these are, I would say, less commonly used either, right? Cell array and structure array. Okay, so I would say that's it for this class, right? We talked about the how we can use MATLAB to solve sets of linear equations in the beginning, and then we talked about these different data types, which can be helpful for us to, um, let's say, create our own database, right? Or analyze the database from other sources, and then to make our own data analysis. Okay, so that's it for this class, and let me know if you have any questions. Thank you.